Hello again, my dear students. Now this is part number 3 in our lecture 4, Semiconductor Pn Junction. If you remember in the beginning of this part, 1 week ago, I have already mentioned to you that now we are transferring, now we are bridging the other side of the river, where we are talking about devices. Here we will start with the most fundamental and the most maybe simple electronic devices, which is just a Pn junction. In the previous 2 parts of the lecture, we have studied the performance of this device under what's called the thermodynamic equilibrium, where there is no external applied force is applied. Now, in this lecture, I will first go to flashback what we have already learned in part number 1 and part number 2, and then I will transfer to part number 3, where we are talking or we are considering our device under external applied voltage, where thermodynamic equilibrium is no more exists. So let me now share my presentation slides and start with you the journey with the Pn junction. Okay, so I believe now you can see my presentation, and also I think I can now also operate my laser pointer. Okay, as I agreed, we will start with a very quick scan related to the performance of a semiconductor Pn junction under a thermodynamic equilibrium in order to refresh our memories, and then we will start building using this information in order to study the performance of the Pn junction where thermodynamic equilibrium is no longer exists. So, if you remember, we start with a very quick understanding about the difference of doping type, where we have an N-type and a P-type doping. An N-type where the Fermi level is more towards the conduction band, and the P-type where the Fermi level is more towards the valency band. And then we are now targeting to combine the N-type region with the P-type region. Here, this is a very important stage that you have to understand very well, my dear students. Here you have to search for a reference, and our reference code, the Fermi level. Let me quickly go to my whiteboard and start with you refreshing how we can construct a Pn junction. So I will stop sharing my screen for a while, and I will turn back here, and we'll start again repeating the process how we can build a Fermi level. Okay, so in order to do it, whenever you are building a junction, start with your Fermi level. First, let me plot the two N and P types independently, just to make them as a reference without why we are doing plots. So, for example, here this is the conduction band, the valency band. Let's for example, make the P-type here. So this is our EF, and usually you have what's called the intrinsic Fermi level here in the middle. So this is EFI, and as far as EF is smaller or is below EFI, this means that this material is a P-type material. And let's do to the other round. So we have here again the conduction band, the valency band, Fermi level, intrinsic, and we have this is our Fermi level, and as far as the Fermi level is above the intrinsic Fermi level, then the material is an N-type. So now we are targeting to combine this N-type region. Sorry, this is the P-type region, and this is the N-type region. So we are now targeting to combine both. As we agreed from part number 1, in order to combine both, start with Fermi level. So first, draw this Fermi level, draw this EF, and then starts to plot or sketch every line in your plot diagram with respect to this EF. So whenever you are plotting your P side, for example, which is the left-hand side here, so you will say that, okay, now EV is more close to the EF and EC is a bit further. So this is a P-type portion. And then here in the right-hand side, you will do the same. Okay, so now this is an answer. So this is EC, and this is EV. So as you can see, here the material is P-type, basically because the Fermi level is more closer to the valency band, and here the material is an N-type because basically the Fermi level is more toward the conduction. So this is how you can plot it in a very easy way, my dear. So finally, the final step is just linking these conductions in valency band in this way. Now we have what's called the overall Pn junction. As you can see, I'm repeating this. We already did it in part number 1. I'm just repeating this because this is a very, very important step in understanding the Pn junction, either under stable equilibrium or far from stable. Okay, so this is the first step in plotting our junction. So this is the first step in implementing our energy band diagram for a Pn. So as you can see from this energy band diagram, let's now start considering some very important observations. Again, I'm repeating this part because this part is very important. So as you can see here, this is a P-type, no worries. This is an N-type. What about this region? The first observation from this region is that this region is a region where there is a tilting in the energy band. If you remember our lecture number 3, where we deal with the drift diffusion model and the energy band diagram under applied voltage, we say that whenever you have a potential, this potential will cause the energy band diagram to tilt. So if you remember, my dear students, if we have an electron here, this electron will drift and go in this direction because electrons tends to have minimum potential, and the potential energy of the electrons goes down whenever you go down. And if you have a hole here, this hole will drift and go to the other side because the energy of holes decreases by going upward. So now we have a potential. However, we didn't insert any external force. We just combined the P-type and the N-type portions together. We did not insert any external battery to our semiconductor or to our Pn junction. That's why, my dear students, we call this as the built-in potential. So this built-in potential is simply a built-in, a natural potential. It's not an external potential. So maybe one of your questions is, how can I distinguish between a tilting due to a built-in potential and a tilting due to an external bias, an external potential, an external electrical field? If you remember, my dear student, the answer is in the Fermi level. Whenever there is no external applied voltage, the Fermi level should be flat. Once you apply an external voltage, which is what we are going to do today in our lecture, this Fermi level will no longer become flat. So when you have any semiconductor devices or any semiconductor junction, and I told you, please check if this junction is under thermodynamic equilibrium or not, what you are going to do simply is to check what is the condition of the Fermi level. Is the Fermi level flat or not? If the Fermi level is flat, then the material or the junction is under thermodynamic equilibrium. So this is simply the first observation. So we have now a region in between the N and P where this region is above and or include the building. This is the first. The second observation is, as I just mentioned, if we have an electron here, this electron will automatically drift and go to this side. If we have an holes here, these holes will automatically drift and go to this side. That's me. There is no probability to find any static charge in this region. Again, there is no probability to find any static charge in this region. Because simply, if you have an electron, again, what do I mean by static charge is a fixed charge. I mean an electron sitting here, for example. There is no probability to find such an electron, because if there is an electron here, it will automatically slide and go to this side. If there is one hole here, it will automatically slide and go to this side. So simply speaking, electrons and holes will not exist more in here in this area, and they will drift either to the right side if they are an electron, or to the left side if they are hole. And accordingly, we call this region a depletion region. Why we call it the depletion region? Simply because no electron, no carriers, no static charge exists in this area. So it becomes an area which is depleted from charge. No charge occurs, or no charge exists in this area. This is actually a very important point, my dear students. We will use it in the last slide in this lecture, maybe in this part or the next part, I don't know. But we will return back to this important point. Now, as you know, this is a Pn junction. So simply, we can say that this depleted region is divided into two regions, what's called XP and what's called XN. So simply, XP is the region in the P side where we have the depleted region, and XN is the region in the N side where we have the depleted region, and the summation of these two regions, what we can call W, where W is the depletion. So we have Xn and XP, Xn plus XP equals to W, W is the total summation. This is simply the energy band diagram for P. Okay, now, let's continue observations related to energy band diagram. And let me now redo very quickly another energy band diagram for the same Pn junction. So this is our energy band diagram, and this is our Fermi level, as you can see. Of course, this is the EF, and this is EC, and this is E. Okay, very good. So let's now start doing this very simple experiment. Now, as we just mentioned, we can divide this Pn junction into three regions. This is a pure P-type region, this is a pure N-type region, and this is a depletion region of its down. Here we have what's called an internal potential, which has which causes actually this tilting, where if you have an electron here, this electron will move in this direction. If you have a hole here, this hole will move in this direction. Okay, so if I told you in the exam, forget that this is a Pn junction, and I just told you in the exam, please define the polarity of the potential here. So this is a very easy task. We did it actually more than one time in the previous lecture, lecture number 3. You have an electron here, and this electron will move toward the right side. That means you have a positive terminal here of a battery, and you have a hole here, and this hole will drift to the to the left-hand side of the junction. So we have a negative terminal here. So it seems like you are connecting a battery, looks like that here. This is a positive terminal connected to N, and the negative terminal connected to P. Okay, so now the question is, this is a built-in battery. It's a virtual battery, something inside the material, inside the junction actually. What if we connect an external battery? What if we connect an external battery to this internal battery, or to this junction? So basically, here you have two probabilities. Either you are going to connect a battery with the same polarity of the building potential. So you are adding a battery in this direction. This is the N side, this is the P side, as I did here. I'm connecting the N with a positive and the P with a negative, and then you are adding to this. Or you will connect a battery in the other direction. So you will make it in this direction. So basically, these are the two main conditions. What we are trying to now to do is to try to understand what if we add a battery like this, or what if we add a battery like this. But before going to do so, please don't forget that this blue battery is a built-in battery where thermodynamic equilibrium occurs. Whenever we will add an external battery source, an external potential, no longer thermodynamic equilibrium. So you will not find this flat energy level no more whenever you add such an external. So in order to make it in a very easy and conceptual way, and in order to get more and more inside the PN junction, let's first start with the thermodynamic case, where we have this blue battery building potential. Again, this is not a battery, it's a virtual battery representing the potential inside the building potential inside the semiconductor PN junction. However, of course, there is no battery inside the PN junction. So what you are going to do is, or what you are going to imagine is as follows. Now, due to this battery, electrons will move from the left-hand side, as you can see, to the right-hand side. And holes will move from the right-hand side to the left-hand side. But please don't forget that in this side, in the left-hand side, electrons are very, very, very few because it's a B-type material. So P is much greater than N. If you remember from part number 1, part number 2, I told you that herein we call this P as the majority carrier, and this N as the minority carrier. So the majority is holes, the minority is electrons. So only a very, very, very few electrons were going to move from here to there. This is simply because the stock of the electrons in the left-hand side is very limited. Similarly, here you have a majority of electrons and a minority of holes. So very, very few amount of holes who are going to travel from the right-hand side to the left-hand side, because simply the stock is very limited. So it's a very limited flow of electrons, which is typically very, very limited current, nearly zero current. Okay. The second observation. Now we understand the process of the thermodynamic equilibrium, where we have motion of electrons and motion of holes due to only minority carriers. The second important point is when you have this electron configuration or this energy band diagram, this tilting in the energy band diagram, this bending in the energy band diagram is simply due to this potential. And we agree that the tilting is proportional to the potential. When you increase the potential, when you increase your battery voltage, this tilting will going to be increased. So simply, if I add a battery in this way, so this battery has the same potential like the building potential. What is going to do what's going to be implemented is that this drift will increase. You are adding more and more potential in the same polarity. So the electrons will going to move in a higher speed. Of course, again, the stock of electrons is very limited, but they will flow in a higher speed because you are giving them more and more positive energy here. So electrons will be attracted more and more negative energy here. So the electrons will be attracted in this way. So let me again start with the thermodynamic equilibrium case. And as you can see, we have here something like that. So this is the thermodynamic equilibrium case. What I'm going to plot now is what if I add a battery from this type? I mean the same polarity like the building battery. What we're going to do? So as I just mentioned, I have here an internal battery which has something like this polarity, and this is N and this is P. Okay, so this is the negative terminal of the battery. This is the positive terminal of the battery. The positive terminal is connected to the N side, and the negative terminal is connected to the battery. Now, my configuration is: what if this PN junction die is connected to an external battery in this way? So as you can see here, you are increasing the total potential. The building potential and your external source are in the same polarity. So you are increasing this total. That simply means that the output will be in this way. As you can see here, if this has a height, which we call it V node, if you remember, this is a building potential, if you remember from part number 2. Now you have a new height, which has V node plus VR, where VR is the reverse voltage applied. This is the external applied voltage. So if you would like to plot now the Fermi level, you will find the Fermi level looks like that. You have now a splitted Fermi level, no longer a flat Fermi level, because this energy bandogram is no longer under equilibrium. So simply what I did is that we add the voltages. Okay, so as you can see here, my dear students, we are just increasing the total charge or the total potential. That's why the height of these, what we can call barriers, have increased. Here, after the increase of this height, you will find that more electron will go to drift here and more holes will go to drift there. However, please don't forget, this is the P side and this is the N side. So the stock here is very limited. The stock here is very limited. The stock of electrons here is very limited. The stock of holes here is very limited. That's why the current moving here and the current moving there is very, very, very low. So that's why we have current, but this current is very, very small because the electron available in the right hand side and the left hand side is very limited, and the holes available in the right hand side is. So this is the first case, what we will call the reverse bias. In the reverse one, when you are going to add an external battery, which is in the same polarity as the building potential, the height is going to increase, and the current is very, very, very small. Now, let's turn to the other scenario. Again, let's start with the thermoequilibrium case, where we have, this is EF, or the Fermi level, and here you have your energy band diagram. Again, the building potential, taking this polarity. So this is the N, and this is the P. The N is connected to the positive, so electrons drift in this direction, and the hole is connected to negative, that's why holes drift in this direction. Now, what will happen if I connect my PN junction with an external battery with this polarity? Now the polarity is reversed. Herein, you should ask me a question. If you remember, we call this height V node, or the building potential. So what is the relation between V node and the volt you add what we are calling V4? What is the relation between these two? Now these two voltages are subtracted from each other because they are with different polarities. So if VF is still smaller than V node, if VF is still smaller than V node, what happens is that the total voltage here will become V node minus VF. So you will have something like this. And again, my dear student, the Fermi level is no longer flat. It will become split into two Fermi levels. Now your new height is V node minus VF. You reduce the height of this voltage, and it becomes V node minus VF. So when I ask you in the exam, please plot the energy band diagram for forward voltage, forward bias. I have to mention, is it forward below V node or above V node? If it's below V node, then this is the case. Then, what if this voltage is greater than V? In this case, my dear students, this barrier will be switched into the other side. So let me better make it in a new slide. So again, this is the original energy band diagram. Now I have a PN junction. The PN junction is connected in a positive, negative way. So this is the this is the other direction because the building potential is in this direction. This is the N and this is the P. So now VF is greater than V node. So you will have something like this. Now, or again, the Fermi level is no longer flat. And as you can see now, electrons, here this is the N type. You have a huge number of electrons. These electrons will drift here. Here this is the P type. You have a huge number of holes. Holes will drift here. So you have a huge amount of current when V4 is greater than V node. So let's recall the story from the beginning. First of all, we have the thermodynamic equilibrium. only few electrons can move from the left-hand side to the right-hand side because this is a p-type. And only few holes can go from the right-hand side to the left-hand side because this is an n-type. So nearly you don't have it. Then you have two scenarios. You have to add a battery in the same polarity of the building potential, or you can add a battery in the other polarity of the building potential. So if you add a battery in the reverse direction, I mean in the same direction of the building potential, but we call it reverse direction. So this height, which is V node in thermodynamic equilibrium, will become V node plus VR, which is the voltage you add. And again, the current is very limited because you are extracting current, you are extracting electron from the p side, which has already a very limited number of electrons. And you are extracting hole from the n side, which is already have a very number of holes. So your current is very, very limited. Then the other condition, what if the polarity is reversed? So I have a forward bias, not a reverse bias. Here you have to ask a question: is this forward bias is smaller than V node or greater than V node? If it's smaller than V node, then simply the height will shrink. So we have a total height of V node minus VF instead of a total height V node. But, and again, still the current is very limited. But what if the current, what if the voltage applied, the forward voltage applied is greater than V? Then this n-type will turn to be in the upper state, and the electron will drift from the n-type to the p-type. Here we have a very huge amount of electrons, so we have a huge amount of current, and holes also will drift from the p-type to the n-type, and then we have a huge amount. This is simply, my dear students, the 4 cases for our PN junction device. So let me now return back to my presentation slides and go directly to the slide where we can show this effect. As you can see, my dear students, here you have V equals to 0. So this is just the V node barrier, and this is again what we have already plotted. So I have to use my pointer. Okay, so this is the thermodynamic equilibrium case, my dear students. The voltage is V node. The voltage is this is only the building potential. This is again the height here is V node. So as you can see, the Fermi level is flat. This is the sign for thermodynamic equilibrium. Now, if you add the potential, as you can see in this case, the potential is forward. So the height reduced to be V node minus VF. If the potential is reversed, the height is increased to be V node plus VF, plus VR, I'm sorry. Herein, this is a case where V node is still, or VF is still smaller than V node, so this is just a reduction in height, and that's it. Okay, so if you remember, my dear students, in part number 1, we have plotted what's called the carrier concentration for the NNP. Now, what we are interested to do is to plot the same graph expressing the electrons and holes, but under either reverse or forward bias. So let's now start together thinking how we can plot the Fermi, the electrons concentration and the holes concentration under this condition. So we are interested now to plot this energy or this carrier concentration in forward and in reverse bias for different configurations. So let's now start doing this. Okay, so let's start with the standard case, the thermodynamic equilibrium case. So we have this is our Fermi, so this is our energy bandwidth. Now I'm going to plot. This is x, or the distance, and this is NNP. Again, if you remember, my dear student, we can divide our semiconductor p-n junction into 3 portions. This is the p region, this is the n region, and this is the depletion region. The total width here is W, this is XP, and this is XN. So now in the P region, life is very easy. In the P region, this is a typical P-type semiconductor material, as you already solve a lot of problems with your sheet 2 and sheet 3 problems. So simply the concentration here is the whole concentration here is equal to Na. So if you remember the notations, we say that this is a P node. Again, P because this is holes, that is a subscript P because we are in the P region, and node due to thermal equilibrium. So PP node equals Na, and NP node equals Na squared over Na. So very simply, you can write or you can plot now the electrons in the hole. So the holes will have a value called Na, and the electrons will have a value called Ni squared over Na. Reversely, in the N region, we have what's called N node, which is the electron concentration in the N side at thermodynamic equilibrium, which is equals to Nd. And we have Pn node, which is equals to Ni squared over Nd. So simply you can solve these both for electrons. You have some Nd, and for holes you have Ni squared over Nd. Now you can make this linking between both groups. Okay, so the drawing code, which we already drew, I believe, in our part number 2 lecture, if you remember. These curves representing the hole and the electron concentration in or under thermodynamic equilibrium. Now, what we are going to do is simply, we are going to replot a similar graph, but under forward bias and under reverse bias. Let's start with the forward bias. And let's start first to think what happened when your junction is under forward bias. So, if you remember, a forward bias means to connect the P and N in this manner. So this voltage is against the building potential. Accordingly, the energy band diagram shifts from being like that to be like that. Now, electrons are moving here and holes are moving there, if you remember. So, electrons are moving from the N side to the P side, and the holes are moving from the P side to the N side. The question is, how this will affect our carrier concentration? This is the same graph we just plotted few seconds ago. This one. I'm just repeating this. How this will affect our carrier concentration? Now, let's start with electrons. For example, this is the P type and this is the N type, so this curve represents electrons. How electrons will be? Now, electrons are drifting from the N region to the P region, which means you are taking electrons from the N region and you are putting them in the P region. Okay, let's turn it to make it with numbers. If Na, for example, is 10 power 15, that means that for silicon, the NP node is 10 power 5. And if this, for example, is 10 power 17, then this will be 10 power 6. Now, you are taking from these 10 power 17 electrons and you are adding here to the 10 power 5. Simple, very simple. That means that these electrons will decrease and these electrons will increase. Very simple, because electrons are drifting from the N side to the P side. So electrons in the N side decreases and the same amount will be added to the P side. However, if, for example, 10 power 5 electrons move from here to there, for example, that means that these electrons will turn to be 10 power 10. That's right, because you take 10 power 17 electron from here and you put it there. So these electrons will turn to be 10 power 10. And these electrons will turn to be 10 power 17 minus 10 power 5. Because here, this is the source. This is where you have pick up 10 power 5 electrons. 10 power 17 minus 10 power 5, this is, we are now subtracting two numbers. The difference between these two numbers is 10 power 12 times, million times. So simply, this is 10 power 17. However, here you are adding 10 power 5 and 10 power 5. So this is will be, I'm sorry, this is not 10 power 10. This is will be 2 times 10 power 5. I'm sorry. So this number is double. So whenever you are going to plot the carrier concentration, it will be like that. Again, this increase in NP, again here I'm not using node because we are not under thermodynamic equilibrium. So this increase in the NP is taken from here. However, we cannot observe, we cannot recognize the decrease here because the decrease here with respect to the stock is very unobservable. It seems like if you have $1 billion in your bank account and I withdraw $1K, then you will feel nothing. This is typically what happens. I withdraw 10 power 5 electrons out of 10 power 17. You feel nothing. However, in the minority side, it's double. That's why the effect appears. So let's now return to my slides. I'm sorry, yes, let's make a full screen. So here you can see what we have already plotted. Now this is the majority electrons, and this is the minority electrons. In the forward bias, the majority electrons will drift from the N side to the P side. The majority carriers will move from the N side to the P side. So the minority electrons will increase. This is the increased amount, as you can see. However, the majority will not be affected. The effect is very neglected. Similarly, holes drift from the P side to the N side. So holes in the minority will be affected. However, holes in the majority will almost keep the same. This is the equation linking this. However, I will not ask you about the equation. I'm just asking you about the concept that we already have delivered using this slide, but I will not ask you about the concept. This is the amount of the holes increase, and this is the amount of electrons increase, as you can see. Okay, so what about the other side? What about if the junction is a reverse bias? Okay, so Again, starting from a thermodynamic equilibrium. If you remember, my dear student, when a junction is a reverse bias, that simply means that this height, which is originally V naught, will increase and will be V naught plus VR. So more minority carriers will go from the MP, this is the P side, and the electrons here are minority. So more minority carriers are going here, and more minority carriers are going there. That simply means that you are taking electrons from a place where the number of electrons is very, 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 very small. So it will be hardly a factor. And you are now taking holes from the place, which is an nth place, where the number of holes is very small. So this number will be a factor. So if we return back to the slides, as you can see here, originally, I will start to open my PowerPoint. Okay, so originally we have this amount of electrons. But due to the reverse bias, these electrons drift to the n side, so the number of electrons decreases. Here, originally, we have this Pn node, but as these electrons go to the P side, the number of holes decreases. Again, I'm just asking you about the concept. As you can see here, V node plus VR, and in the previous slide, I think it's V node minus V. Okay, so this is generally the conditions. Now, let's start to combine all these conditions together. And let's start to focus generally on the device, which is the Pn junction. So, generally, we have 3 regions of operation. Generally, we have 3 regions of operation. This is slide, my dear students, is very, very, very important. Let me start first with here. Okay, so this Pn junction if V is equal 0, what I mean by V is the external voltage. So I am under thermodynamic equilibrium. Then, automatically, you don't have current. Okay, so if we are plotting here, if we are plotting here, this is the voltage, and this is the current. So whenever the voltage is 0, the current is equal to 0, which is very large. Now, if we add a reverse voltage, what I mean by reverse voltage is simply that this Pn junction is connected in this manner. It's the same direction of the building potential. So you will have an energy band diagram looks like that, if you remember. Only the minority carriers, which is the electron, will move here, and the holes will move there. So the current is very, 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 very small. You have a very small current. So whenever the voltage is negative, what we call the reverse voltage, the current is very limited, very small current. Now, in the forward bias, we have 2 conditions. The first condition is to have V forward smaller than V naught. So the corresponding energy band diagram, if you remember, my dear students, is something like that. This height is somehow decreased, but still the current is not able to move because we still have a height which is V naught minus VR. And finally, if Vf is greater than V naught, then the device is turned to be in this manner. And a huge amount of electrons will move from here to there. So in this curve, we have to set the point V naught, which we call it the building potential. And then we have to make something like that. So if your voltage is, if your forward voltage is smaller than V naught, very small amount of current because you still have this barrier. If V naught if V4 is greater than V naught, then the current will start to increase in a very rapid manner. And this equation is very important. I equals to I naught e power V over Vt minus 1, which is the diode equation. This equation occurs when V forward is greater than V. So basically, here we have 4 regions of operation. The first is under thermodynamic equilibrium. Voltage equals 0, current equals 0. The second is under reverse bias. Very few amount of current. The third is when the voltage is forward but still smaller than V naught, then the current is still very limited. And finally, when the voltage is forward and greater than V naught, then the current starts to increase exponentially, as you can see. So these are the main 4 regions of operation for a PN junction diode, and this is the curve demonstrating. Circuit-wise, this diode is represented in this manner. And why we are representing the diode in this manner? Because simply, as you can see, it's a one-directional switch. What I mean by one-directional switch. So, if the voltage is greater than V naught, the current will move, and will move in a very, very high speed, and a very, very increasing manner. But if the voltage is smaller than V naught, you nearly have 0 current. So, current will pass only if the P, this is the P side and this is the N side. We call this cathode and anode. So if the voltage here is positive and this the voltage here is negative, which is a forward bias, then the current will move, which is the same direction of this arrow represented by the diode center. If the voltage here is positive and the voltage here is negative, which is the reverse bias, the current will not move. Very few amount of current, which is nearly 0 current will move. So it's a one-directional valve, let me say, which is the PN junction, our first important device. So let me now turn back to the slides. And again, here you can see that presentation of the IV curve. Again, this is the exponential current. I is proportional to the e power V over KT, as you can see here. I equal I naught e power minus e power 3 QB over KT minus 1. By the way, if you remember, we already have mentioned that KT over Q is what's called the thermal voltage. So that's why I'm calling here VT, which is the thermal voltage. If you remember, this is 25.9 millielectron volt at room temperature. So this is what we call the forward bias, and this is what we call the reverse bias of junction. Again, these equations is not required for you. It is just for demonstration. You can have the full detailed step-by-step revision in your lecture script. You can find the lecture script still detailed step-by-step revision. However, I'm not asking you about revisions. I'm not asking you about equations. Just in case you need this equation, it will be given for you as in the formula sheet. So this is the case for the PN junction. Now, we have a 3 important concepts by the end of this lecture we are going to consider in this lecture. The first one is what's called the breakdown voltage. What is a breakdown voltage? As you can see here, we demonstrate our PN junction diode in a form of 3 regions. Or I'm sorry, 4 regions, because this point, this origin point is a region, which is the thermodynamic equilibrium. One of my final exam questions 2 years ago was, and I gave you this IV curve and told you, please highlight where the thermodynamic equilibrium is this curve. So simply, it's a point where voltage equals 0 and the current equals 0. This is thermodynamic equilibrium. This is the origin point. So this is the origin point. This is the thermodynamic equilibrium point. And then we have this region, which we call it the subvolume potential region, when the voltage is still smaller than V naught. And then when the voltage is greater than V naught, the current starts to increase exponentially. This is the forward bias. And if the voltage is in the negative direction, this is a reverse. But what about this region? What if I keep on increasing the reverse bias voltage? What will happen? What will happen is called the breakdown. That you reach a point at which your diode will break down. So we call it VBD, or breakdown voltage. This breakdown voltage can occur due to two reasons. One is what's called the Zener breakdown. The Zener breakdown is simply because when the depletion region becomes very, very flat, so that as you can see here, the electrons in the p-type and the or the valency band in the p-type and the conduction band in the n-type become somehow aligned. So electrons can jump from here to there, creating a huge amount of current in the reverse direction, and this occurs the breakdown. And the second is what called the avalanche breakdown, when this slope is very, very, very high. So electrons are moving in a very high speed. In this case, electrons can break another bond, and as you can see, this is a one electron. When it hits an atom, it broke a bond and creating another electron, so it becomes two electrons, and then these two becomes four and so on, and then the current increases rapidly. So the breakdown voltage can occur either due to the Zener effect, where electrons in the valency band of the p-type region jumps to the conduction band in the n-type region, or due to the bond broken through a very high-speed electron due to this high electrical field. Usually this electrical field is something like 10 power 5 or 10 power 6 centimeter per, volts per centimeter to cause such an incremental. Finally, which is the final slide in this lecture, which is actually a very, very important slide. Let me now return to this equation. If you remember this equation, this is what I believe the terminating slides in part number 2, if you remember. So in this equation, I told you that this is the depletion voltage W, and this is the region in the N side, and the region is the P side, XN node and XP node. And I told you that this is, we simply put this node terminal to indicate that this is under thermodynamic equilibrium. But what about reverse and forward bias? Life is very easy. If you are in a reverse bias, what you are going to do is very simply, is that you are going to use the same three equations, but with V node replacing by V node plus VR, if you remember from this slide. So whenever it's a reverse, it's a V node plus VR, as you can see. Okay, so simply using the same equation, but kicking out this node terminal, because no longer thermodynamic equilibrium, and then you put V node, and then you replace V node by V node plus VR. What about if you are a forward bias, then you are replacing V node with V node minus VR. So in a very simple manner, this V node will be turned to be V node minus VR. But what if VF is greater than V node? As you can see, this X or this W actually is under root. So if you are replacing this V node by V node minus VF, and VF is greater than V node, then W will turn to be imaginary. That's simply because when VF is greater than V node, you don't have a depletion region. So the depletion region exists if you are under thermodynamic equilibrium, you are under reverse bias, you are under a forward bias, but VF still is smaller than the building potential. These are the three cases where you have a depletion region. However, when the forward bias is greater than the building potential, you don't have actually a depletion region. That's simply why this W turns to be imaginary. Finally, if you remember, my dear students, told you that this is called the depletion region because this is a region where you don't have carriers. You don't have moving electron or moving electron or holes. Because simply, if you have an electron here, it will drift to the right-hand side. If you have a hole here, it will drift to the left-hand side. Very simple. So, if you start now to imagine your PN junction diagram, you will find this form. Let me make it using a new slide. Okay. So I believe you already hate this energy band again for PN junction because we plotted millions of times. So this is the energy band diagram. Now again, divided it into 3 regions. This is a p-type region, where you have a lot of heat. This is the n-type region, where you have a lot of electrons. And this is the depleted region, where there is no electrons and holes, because simply electrons will go to this side and holes will go to this side. So, what you are going to do now, let's think about this device in a different manner. You have 3 layers. You have 3 layers. One layer is somehow conducting. It's a semiconductor, but it's a gold, so it's somehow a conducting layer. And another is a conducting layer. It's an n-type dot. And the third one is somehow an insulator, because it does not contain free charge. This is the definition for insulator. If you remember in part number 1, I believe, I told you that you please don't forget that this depletion region becomes or turns to be a depleted region, which is some type of insulator. So you have 2 conductors, and in between you have an insulator. So this is what you basically call capacitor. So in this PN junction, my dear students, we have what's called the capacitor capacitance effect, or a parasitic capacitance effect. So let me share my presentation slides again. And let's move to the final slide here. This is the equation representing the capacitance. Of course, I will not ask you to memorize this equation. Of course, this is not asked. If you need it, we will use it. Actually, this is the very simple equation for a capacitor. You already know, which is epsilon A over W. I believe that you already know this equation from your physics classes, maybe in prep or in high school. So epsilon is the permittivity of the material, equals to epsilon naught times epsilon R, where epsilon R is relative permittivity. A is the area and W is the width. We already, my dear students, have an equation for W, as you can see. But what I did here is just I replaced this V naught by V naught plus VR, as you can see. That's all. So this is simply what we did in our equation. So as you can see, this is the capacitance format. If you know this equation, and if you have W is given, then you can directly substitute by epsilon A over W and get this equation in the way you are, or in the way you need to solve your problem. Simply, this is the termination of the PN junction lecture, one of the very important lectures in our course. So I believe, or I hope actually, that you have understand well this concept. Please go through these concepts step by step, very carefully, and try to understand it in a very good manner, inshallah. Thank you very much for your concentration, and let me hope to see you again the next week, where we are going to talk about the most important electronic device ever, which is the metal oxide semiconductor field transistor, the building unit for any and every semiconductor electronic devices we are currently using. So thank you very much for your concentration. See you next week, inshallah.